Hey guys, how y'all doing?
Very good. How you doing yourself?
Good. Doing okay. I'm wearing my Minnesota shirt that's got tie-dye and can be better than that, I guess. Some of you may disagree, but that's okay. Certainly I seem to clash with my background, but you know what? Life's too short to worry about those sort of things. Okay, a couple things I want to mention by way of announcement and then sort of maybe get into content for the day. Um, First off, yeah, we got an exam coming up. I've got it scheduled to release tomorrow, right after class is over, and then you'll have well, let's think, 11, 35 hours almost to sort of get that figured out. Okay. I think a lot of you will probably want to sort of after the review is over, because the review will go over those sample exam questions that are on Canvas now. But after the review is over, you want to go spend some time studying up with people in your lab groups, your previous lab group, or people you know, and just sort of feel comfortable with the material. And then when you're ready, just go ahead and take it at your convenience. One key thing is you're not supposed to communicate to other people in any way, shape, or form about the content of the exam. And that will be a challenge for at least two of you in particular, because if you're related, that's really hard to not talk. But again, I can run code that will check on what you've done in terms of your answers. And just do your best to not cheat, because cheating sucks and I really don't like the paperwork. Okay. Second thing I want to mention is the homework assignment that was due yesterday, because I only yesterday morning let you know about when it was due. I bumped it until today at 11:59 p.m. If you think, oh, damn it, I uploaded it and I uploaded it a little bit earlier, now I want to revise my answers, fine, go ahead and redo that. That's okay. But the problems assigned yesterday correspond to yesterday's class session, plus then what we're doing in class today in chapter 2, section 3. And you should feel comfortable with that material, comfortable enough to upload your answers by midnight tomorrow. And indeed, I would feel comfortable with that material before taking the exam. Just to let you know about the timing of things, if you are thinking about timing, okay, the exam, not the exam, the answers to the homework problems that are due out of chapter 2 by midnight tomorrow, 11:59 p.m. On Wednesday, those should be available Thursday morning. I'll upload the answers Thursday morning. And so if you want to look over the answers to those problems before working on your exam, don't plan on sort of taking the exam until Thursday afternoon. Yes, we will have moved on into chapter 3 material by then, but we're going to do some of that today. And the lab today will correspond to chapter 3 content. The lab today will not be corresponding to material on your exam, but it's still due by midnight tomorrow. Willow asked, are the supplemental questions listed under homework 1B required for points? Okay, so supplemental refers to the section where they're from. So at the very tail end of chapter 1, you'll see supplemental problems from all of the different sections in chapter 1. And in the supplemental problems in chapter 2, yeah, I'm saying turn them in for points. If the grader chooses to grade those questions, those count for points. It's supplemental in the sense that it's, again, not from a particular section of chapter 2. Okay. So I think that answers at least one question. You may have some questions related to administrative things. Now's a great time to unmute or raise your hand or type if that's the sort of thing that you need to do, prefer to do. Well, there's always going to be other questions that do come up naturally during the course of class. And if I don't see them in the chat, definitely unmute and let me know. How about questions related to subject matter material from yesterday? Things like a mean, a standard deviation, or even an expected value. Okay. So what I love to do is to dive in on new content to really finish up chapter 2, section. There's another example I like to provide to you in chapter 2, section 1 and 2, section 2, and that is the Poisson probability distribution, finding the mean and then finding the variance of that distribution. And then we'll move, because we sort of tackled chapter 2, section 3 problems yesterday. I'd like to move into chapter 3, sections 1 and 2. So let's do that by sharing the screen, and let's do that desktop. And what I'm wanting to do is maybe move this over here off to the side so I can see the screen and see a couple of you, perhaps, if you are on camera. Okay, so if I remember from last time, one of the things we noted was that if you have a probability distribution that's discrete, we defined the expected value or the average the following way: mu of x. So this is the discrete case. I guess mu of x is just summing across all the possible x's, x times then the chance of that x value occurring. Let's consider the Poisson distribution, where we know the probability of the random variable x equaling lowercase x, sometimes we've called that just p of x, is equal to e to the minus lambda, lambda to the x power over x factorial. Okay, so let's find the mean of that Poisson distribution in general for any given value of lambda. And again, you know, lambda is related to the mean in some fashion. Okay, so we're just going to be summing x goes 0 up to infinity, because all of the possible values that are non-negative integers are possible for Poisson. It's just the number of occurrences of a situation in a given amount of time. And so if you wait long enough, you could have an infinite number of occurrences, or maybe you'll have none if the mean is low. So we're going to have just x times p of x, which we know e to the minus lambda, lambda to the x power over x factorial. And I'm spotting algebra, and I happen to know a couple statistical tricks from probability that I think they're helpful to get used to seeing these sort of tricks. Okay, so the only reason I'm mentioning is not in this class on an exam, but rather in your later coursework. You're going to sometimes say, oh, yeah, that's something I know, and I can simplify in a place where earlier you might not have been able to see how to solve a question. Okay. So I think here we've got an x factorial in the denominator and an x in the numerator. It seems like because x factorial could be written as just x times x minus 1 factorial. That's actually sort of the definition of it. Let's just re-express it in that way, and I'm going to go ahead and write it in. Well, I'm going to do the simplification. I'm summing x goes 0 up to infinity, x times e to the minus lambda, lambda to the x power over x times x minus 1 factorial. And I can cancel out the x in the numerator and the denominator. And I'm summing, again, x goes 0 up to infinity. Okay. Or can I do that? Yeah, let's just, well, okay. So I'm just going to go ahead and do that times e to the minus lambda, lambda to the x power, and then x minus 1 factorial. Okay. So what I'm spotting now is a bit of an issue here, because I guess I had x going 0 up to infinity, and now I still have 0 going to infinity. But if x is -1, -1 factorial is sort of an awkward thing. Maybe I should just go ahead and replace that x minus 1 with y. Okay, so maybe I'm going to go so instead of writing x minus 1, I'm going to call that y, or x would be y plus 1. So I'm going to go ahead and rewrite these two equations here. according to something now I can sub in for x. I'm going to sub in a y plus 1. I'm going to have x is y plus 1. So I've got y plus 1 over here. And well, if x is y plus 1, then I subtract 1 from that. I'm going to get a y factorial. And I'm going to just choose to write that conveniently is I'm going to pull one of those lambdas out front and times e to the minus lambda, lambda to the y over y factorial. Okay. And the range of the summation, if x is y plus 1, I'm going to have y being here up to infinity. I'm going to be careful here. I'm going to just say the x of 0 case drops out, okay? And then, because we have just the x out front, yeah, that's where I was missing something. Notice that we have the x there and the x minus, okay, no, that dropped out. Okay, I want to go back and be a little bit more careful here. And I'm going to erase just a little bit and sort of do something in a way that you're as a group going to say, okay, that seems kosher, whereas you were maybe thinking I was skipping something important here. Okay, you would have been either right or close to right. Okay, so here's what I want to do. I'm going to rewrite this now as that's equal to x equals 1 up to infinity of x times e to the minus lambda, lambda to the x over x factorial. Okay. Yeah, and that's sort of straight from there, so we don't even need that. Okay. So now that we've got this rewritten, and why is this a legitimate thing to do? Well, if x was 0 for the first case, x being 0, zeroes that whole thing out, I could just have that sum being from 1 up to infinity, and it doesn't change a thing. Okay, so that's kosher, entirely legit. And what I want to do is now work with this version of the equation. And I'm going to go to the next page and then continue my work. Okay, so mu of x. Okay, mu of x. Mu of x is just summing x equals 1 to infinity, x times e to the minus lambda, lambda to the x over x factorial. But again, here we're going to write x factorials, x times x minus 1 factorial. And and I'm also going to then do a little bit of work here. Let's just do that step first. And so I've got x times e to the minus lambda, lambda to the x over x times x minus 1 factorial. Okay, and that is x goes 1 up to infinity. And like we saw before, we could cancel out the x in the numerator and the denominator. And we've got now x goes 1 up to infinity, e to the minus lambda, lambda to the x over x minus 1 factorial. Okay. Okay. And then now is when we are going to do our little bit of magic with our summing and say, well, let's have y be x minus 1, or yeah, let's just have y be x minus 1, or I guess I could substitute in for x, y plus 1. And we could now write that as summing y goes 0 up to infinity, e to the minus lambda, lambda to the y, now times another lambda over y factorial. And that lambda over here off to the very right, I could pull that out front, and that's just lambda times now summing y goes 0 up to infinity, e to the minus lambda, lambda to the y over y factorial. And you might say to yourself, that whole thing looks familiar. So that's a times. That whole thing there is the probability distribution of a Poisson random variable. So if y were a random variable, that's Poisson, That set of the sum of those things is going to be equal to exactly 1. Okay, that's exactly 1. Exactly 1. So what we have here ultimately is lambda is the mean of our Poisson random variable. We said earlier lambda is related to the mean. You might have even noticed from the lab the other day that lambda seemed to be really always close to the mean, but indeed lambda is the mean. Okay. Any questions about that? Okay. So I'm again saving these things, and if you ask me to upload them, I can. But I think it's sort of a cute little way of doing something. And what's especially cute about it is that chunk right there. Yeah, literally, I'm able to tell you that the sum over an infinite number of values, because they're probability values from a probability distribution, that sum is exactly 1. And so we find mu is just lambda. The mean of the Poisson variable is lambda. Second thing I wanted to note is we defined yesterday sigma squared, the variance for a probability distribution that's discrete, as equal to the sum of x minus mu squared times p of x. And again, that's over all the x's that are possible. And I'm going to note that that's equal to the sum of x squared times p of x minus mu of x squared. Okay, so if we find the sum of or the average of x squared and then subtract the average of x squared, that should be indeed equal to the variance. Okay, so let's rewrite that. Maybe mu of x squared minus mu of x squared. Okay, so let's go ahead and maybe try that for, let's even verify first that that's even true. So our definition here for the variance, I guess I could FOIL out my x minus mu portion. And that's just x squared minus 2 mu, those are both constants, times x, which is the variable, okay, plus then mu squared times p of x. And so that's going to be distributing the p of x across the 3 terms in our summation, okay. I'm going to have that's just x squared times p of x, and that looks familiar over there. Minus 2 mu times the sum of x p of x plus then mu, and then mu, I guess we're going to multiply by the sum of p of x. And the sum of p of x is always equal to, like we talked about earlier, 1. Okay. The sum of x times p of x, that's just mu. Okay. And so, hey, that's actually sort of a slick thing that here we've got the sum of x squared times p of x minus 2 mu times mu, that's 2 mu squared, plus mu squared there, plus mu squared, plus mu squared is equal to the sum of x squared p of x minus mu squared. Yay. Okay, so because I already know the Poisson variable's value for mu is lambda, to find the variance, I have to only find then my sum of x squared times p of x. Okay, so let's switch to the next page. Any questions before I switch? Okay. Oh. Okay, so for Poisson, I'm going to find sigma squared equal to the sum of x squared times p of x minus mu itself squared. And I know that is already mu is just lambda. Okay, so I need to only find the sum of x squared times p of x for the Poisson distribution. So sum of x squared times p of x is going to be just, well, again, I goes 0 up to infinity. Let's rewrite that as the sum of I going 1 up to infinity, x squared times e to the minus lambda, lambda to the x power over x factorial. Okay, so same trick as before. The 0 cancels out the summation. And I'm going to plug in x factorial equal x times x minus 1 factorial. And so that work gets me x squared times e to the minus lambda, lambda to the x over x times x minus 1 factorial. And that guy goes 1 up to infinity. And I now have, well, I could cancel out one of the numerator x's pretty quickly. This is going to be just summing I goes 1 up to infinity, x times then e to the minus lambda, lambda to the x over x minus 1 factorial. And like before, you're going to say, let's have y be x minus 1, or if you will, x plus 1 is y. So now I'm summing over y goes 1, 0 up to infinity, y times e to the minus lambda, lambda to the y over y factorial. And that's going to be actually multiplied by, remember how we have the y is x plus 1 or y is x minus 1? Yeah, we've got another lambda from right there. So I'm going to pull that lambda out in front like we had done before. But that is really familiar here, because that's just something y goes 0 up to infinity, e lambda, y goes 0 to infinity, y e to the minus lambda, lambda the y over y factorial. That is the mean of the Poisson distribution. Again, the variable times then the chance. So that's just lambda squared. Oh, hold on. No, I don't want to do that just yet. Sorry. Nope. No, let me back off that a little bit. Okay, so I'm going to again do my trick. Y, I'm sorry, there we go. Lambda times now, I'm going to sum y goes 1 to infinity, y times e to the minus lambda, lambda to the y over y factorial. And I'm getting caught in a loop here. Ultimately, I want to end up with lambda squared plus lambda. So that way, when we subtract out lambda squared here, you're going to end up with lambda. And I think I ended up in a place where
I think your substitution went wrong, like the line above,
yeah.
where
Okay, good.
you just said x is equal to y, I think. When you went from x minus 1 factorial, set that equal to y factorial,
Yeah.
and then on the other x, you just set that equal to y, which I
Yeah. But no, I and that's indeed probably where the issue came into being. And it probably is going to be something out front, like a lambda plus 1 out front is what I needed to get. So I think you're right that then I won't say that's where a miracle occurs here, but that is where the issue occurs. And if you okay, as a group, I'm happy to sort of diagnose this a little bit more carefully. And I think you're right exactly where the problem exists, but um, I could also move forward into the chapter 3 material which is closer to the content of the lab. What do y'all want to do? Do y'all have a strong preference? Or any preference, even if not strong? Because
the content closer to the lab would probably help us more.
yeah, I think so. And the thing is, I'm not on an exam. I'm going to be asking you to do a derivation or asking you to prove a binomial variance or anything like that. Although that's one's written up in the book quite clearly. It just seems like if you could see it once, it's a good thing. And so what I want to do is go back and see if I can figure this out and write it up, and then just and put it on paper for you and upload that later to sort of fix this problem. So fix later is my list of things to do. Okay. Okay, so let me open this up again. And then move forward with our content and do that by, okay, come on. And cancel that. Okay, so again, yes, I have to stop sharing and restart. Okay, but that's okay, because I wanted to right around here move forward in the content and start to talk about scatter plots and correlation. And so maybe I'll go again and share the screen. Stop. And in chapter 3, section 1, and 3.2, scatter plots and correlation. Now, we've already even done a little bit of work with scatter plots, and you've seen them before a lot. And frankly, the word correlation, you've all used before, even if you haven't seen a formal definition of the correlation in the context of a scatter plot. But we should probably get into the material as though it's new, because providing definitions is really rather helpful, okay? And so let's sort of go with a simple problem and talk about how to deal with the data and attempt to show a relationship, because indeed scatter plots are to sort of see what is the nature of the relationship if you only have XY pairs and can plot on the x-axis the x value and on the y-axis the y value for each and every individual value in your data set, like x1, y1, you're going to plot there, or x2, y2, x3, y3. And if over a collection of points in the scatter plot, you see a pattern, you'd say, oh, yeah, I can now describe and explain the pattern in some fashion. And there may be numeric summaries for a scatter plot, like a correlation, in the same sense that a sample mean could summarize a histogram. The sample mean tells us the central value in a histogram. The sample standard deviation tells us the spread in a histogram. Maybe a correlation could describe some characteristic of a scatter plot. Okay, so let's go ahead and look at how to calculate a scatter plot in the context of GMP. And these are data that I looked at and discovered earlier today. And I was thinking, hey, this is a rather good example for this class, because y'all are from different areas in engineering. And I think one of the best things to do by way of example is present only things that y'all are somewhat familiar with or could imagine doing. And so I'm trying to sort of lean towards examples that are in that realm. And I asked a group of Stat 130, that's like statistics for history majors in journalism, okay, back in the early 2000s. So shoot, before you were born, I asked a collection of students, how tall are you in inches, okay? What is your head circumference in inches? And that's sort of a goofy thing to ask people, sure, but and I asked them to sort of walk out into the hallway in the computer science building and use a tape measure and do a standing broad jump and see how far they could jump from the very tip of their toe when they took off until the very where their heel landed, if they landed indeed on their feet. Okay, and you've seen with Graph Builder before me create some scatter plots, but Graph Builder indeed could be used to create a scatter plot. And because we're more oriented towards mathematics than economics, we tend to put what we would call the response variable, if there is one, on the y-axis. And it's easier for me to believe that a person's distance that they can jump depends on their height than it is for me to believe that their height depends on the distance that they can jump. You know, maybe we could do a prediction question, like literally, could I predict how far you could jump based on your height? In which case I might swap the role of the x and the y variables. But I think the distance that you jump more naturally could be viewed as depending on a person's height. And we are given a scatter plot. By default, you get this wiggly little line, and with this spline fit, you could sort of make it really wiggly or pretty darn straight, or you could even just remove it. We don't need to have the line drawn in. But here's a scatter plot, and everyone in the class is shown. And within JMP, you can sort of even highlight an individual. And when you highlight that individual, it sort of shows who that was. That was the 27th person who jumped quite far and was on the shorter side, or they lied about their height. I don't know which it was. Maybe they don't know what their height is, because 60 inches seems a little on the short side, doesn't it? Some of you should be doing math in your head and have already hit, oh, that's a 5 foot tall adult male who jumps 90 inches. That seems a little bit off. However you want to slice it. I just wanted to sort of note that JMP could allow us to highlight individual data points. You can highlight multiple data points, even if you think, you know, these are unusual values. Who are these people? We can highlight them and look and see if there's something unusual about them. Okay. I can, however, remove the highlighting. And if you sometimes have some of your data points in a scatter plot darker and then others are lighter, it usually means one row was highlighted. And if you don't like that, you could go ahead and turn that off. So here's my scatter plot. I would call this a positive trend, because the taller a person is, the longer they seem to be able to jump. But that's a positive trend on average. I would even describe this as a linear trend, and some of you would pick a fight with me because you're more influenced by mathematics. But I would say, okay, it's a positive trend on average. Let me try and justify what I mean when I say linear, okay? I'm really thinking something like this. If we were to take the data set and divide it into, say, the lowest fourth of the individuals, the next lowest fourth, the third lowest fourth, and then the highest fourth of the individuals, if I found the average value of the y value and plotted that, and then same thing for the second, and then the third, and the fourth groups, do I have about a straight line across those four means, the means of each of the four groups? Or I could try, if I had enough data point, 5 groups or 9 or 10, essentially, if I'm finding the mean of many data points at a time and then plotting those means, as long as the data points are divided into the lowest, the second, third, and fourth highest groups according to the values x, I would say that is a straight line-ish trend. Or like we noticed before, if I drew in a straight line here, would you say, ah, yeah, that captures the general trend? If you think straight line captures the general trend relatively well, say it's linear, because we're statisticians. We are not mathematicians. We don't need every single data point to be on a perfectly straight line before I would call it linear. I'm going to call it linear if there's an XY relationship where straight line captures the general pattern, okay? So scatter plot. Scatterplot is your friend. It helps describe characteristics of the data. There is, however, the correlation coefficient, and let's talk about the correlation coefficient. R, the correlation coefficient. Sometimes it's referred to as just the correlation between X and Y. And it's a measure of the amount of linear association between X and Y. And let me say that slowly and write it down. R measures the amount of linear association. between X and Y. Okay, so I want to sort of give you an equation for the correlation coefficient R. And then I'll bring back our scatter plot friend and then describe it, the equation with the scatter plot to help us. R is defined to be 1 over n, so 1 over n, sort of like the average. So it's the average of something. It's the average of, well, x minus x bar over the standard deviation of the x's times y minus y bar over the standard deviation of the y's. Now, if I'm going to be real careful, I goes 1 up to n, and that's xi minus x bar and yi minus y bar. Okay, so in the context of our scatter plot, and let's see if I can find my scatter plot friend. Is that downstairs? Yes, let's bring it upstairs and resize it. Let me go ahead and hit done. And let me move it over and it's smaller. Perfect. And now my friend, the scatter plot, return my scatter plot to me. Okay, so there's the scatter plot here. Inside my equation, I'm spotting first off, we're comparing x to x bar. And so that term will only be positive if the average value, if the value of x is above the average. And so if I remember that the average of x is approximately there, I'm sort of thinking this vertical line defines us into positive x greater than x bar or negative x less than x bar. Okay, and if you're right on the line, you got a 0 value for everything in that first parenthesis. And I apologize, there's a square there. There should not be a square there. Correct your notes, please. That's, well, the second portion of the product here is y compared to y bar. And so maybe if I have indeed, in addition to x bar here, I've also got y bar shown. The y's that are greater than y bar will be upstairs, and y's less than y bar downstairs. And in this first quadrant, okay, labeled maybe quadrant 1, we're going to see that we've got a positive times then a positive, okay, which will result in a positive product. If we're in the second quadrant, we've got x being below x bar, so we're going to have a negative times then a positive, which would result in a negative for that second quadrant. The third quadrant over here, quadrant 1, 2, 3, we're going to have, well, x is below x bar and y is below y bar. So we're going to have a negative times a negative, which results in a positive. And in quadrant 4, you have IV. We're going to have x being above x bar, so that would be a positive. But y is below y bar, that will result in a negative overall. And so first and third quadrants give us positive contributions. And second and fourth quadrant items, second, will result in negative contributions. So you could sort of think on average, how far out into the quadrant are you, but also which quadrant are you in? I tend to think of R as corresponding to positive when we have, like here, the data mostly in the first and third quadrants. But if the data were mostly in the second and fourth quadrants, we would have the correlation being negative, because it would correspond with a negative slope or a negative trend of sorts. Okay, so I do not want to even talk about how to do the calculation of that one by hand, but there may be a homework exercise that's short and asks you to do that. And I just promise you that if I were to ask you to do that on an exam, it would be integers, where the means are integers, where the standard deviation is probably going to be an integer, and it'd be very quick to calculate. I probably wouldn't read too much into doing these by hand, because you can see in a second that our data will allow us to, with JMP, quickly calculate what we need. Any question on the concept before I do the calculation within JMP? Okay, so let me go ahead and clear that and show you how to get JMP to do the calculation, because it really is straightforward. It's under analyze. Like everything we do seems to be under analyze. or a graph builder, but analyze, this one will feel a little bit funky at first because, you know, analyze multivariate methods. That sounds fancy. Multivariate. So analyze multivariate methods, multivariate. And the lab has these instructions built into it. So analyze multivariate, multivariate. So if you forget on a midterm how to do this, you're thinking, oh, it's in the lab. Analyze multivariate, multivariate. Just remember what lab corresponds to something. All the GMP instructions will be there for you and available. So analyze multivariate, multivariate. Well, I'm going to just drag my jump distance, which is along the y-axis, and my height, which is along the x-axis. I'm going to put both x and y into my list of variables that I'm going to correlate. I click OK. And I'm going to get a lot of output here, some of which is graphic in nature, and it's even too big. When I say graphic in nature, I mean, you know, there's a graph shown, not that it's like, you know, R-rated or anything. But we get the scatter plots that we had just produced, both y, jump distance, plotted against x, the heights, but also, I have the jump distances along the x-axis and then heights along the y-axis. And so we've got sort of a mirror image here. The correlation between jump distance and height is 0.3097. And the correlation between height and jump distance also 0.3097. Hey, not bad. Not bad at all. So we can quickly get our correlations in sort of a happy way. Okay. Let's think about this conceptually. If I had measured the jumping distances in centimeters and height in centimeters instead of inches, would the picture, the graph, be the same picture exactly? With maybe the x and y scales changed? If I multiply each of the values by 2.54, would my result be identical? Yes. So you'd think, because the correlation is a measure of association of a scatter plot, it might not depend on the units. Well, let's even verify that that is the case. Okay. So let's maybe turn to black and then say R is again 1 over n times the sum of x minus x bar over then the standard deviation of the x's times y minus y bar over the standard deviation of the y's. If I have x bar increasing the same way that x increases, if the mean is dependent on the individual data values, that should have the case. It should be the case. And if the standard deviation also increases, it looks like we're going to have x in inches. I'm going to have inches minus inches divided through by inches. The inches will be canceled out entirely. Okay. Same thing for the jump distances. Inches minus inches over something in inches. The units are canceled out. Correlation doesn't have units. And because correlation doesn't have units, it shouldn't depend on the units. Remember, x minus x bar over the standard deviation of x is just the number of standard deviations above x. I'm sorry, above x bar that the data point x is. This is just the number of SDs, or SD of x, that x is above x bar. Okay, so yeah, literally we're stripping the units away entirely. Okay, so that's sort of a fun feature about correlation. Okay, it is unitless, and it's interesting also if you change the role of x and y entirely. I'd say the correlation between x and y should be equal to the correlation between y and x. Again, because we're stripping units out entirely, and you could swap every x for a y in the equation and the result is the same. You have exactly the same correlation, regardless whether it's with x on the x-axis and y on the y, or vice versa. Okay, any questions about correlation? Okay, so there's one more thing that I think the lab will get into, but I want to sort of push you towards tomorrow's class session above and beyond anything that you might come up with by way of questions from the sample exam. If we get into it, we're going to move forward into regression and using a scatter plot to predict y from knowledge of x. Let's change gears a little bit and consider a different data set. And this is a data more from, I guess, a forestry context, but the volume of harvestable wood that you get from a tree may have something to do with the height of the tree. It seems like it stands to reason, but also the diameter of the tree. But let's work with volume and height. Okay. With Graph Builder, I would want to pursue the question: how does just the volume of harvestable wood depend on the height? So how many board feet do we get out of it as a function of the height of the tree? And I would say, well, I could make it a straight line, but some of you'd say, well, I don't know, it seems a little curved. Doesn't it seem a little bent? I'd say that bent line here sort of more appropriately describes the trend than that straight line. The straight line seems to be not quite as good, okay? But that's just me. You're welcome to come up with your own way of describing the relationship. I also just happen to know something about wood and harvesting wood for the sake of a tree, you know, sort of like creating boards from trees. Hang out with forestry people, you get to know all sorts of weird stuff. But I would describe this trend as maybe a little curved, okay? But still, could I use height to predict the volume of wood that I'm going to get from a tree? I'm thinking so. And I'm going to bet that our, well, multivariate, so analyze, multivariate methods, multivariate. I'm going to bet that height and volume are going to be correlated with each other. And indeed, the correlation here is 0.5982. And indeed, the volume of wood you get from a tree has something to do with the height of the tree. And it looks as though a general trend overall, and if correlation measures the amount of linear trend, if I've got a linear trend of about like 0.6, I'm thinking I should be able to fit a straight line for the sake of prediction. So I'll tell you a story to close out the day, and I won't have to tell you the story tomorrow. Y'all heard of the asteroid series? I mean, I haven't looked y'all up, but if any of you are aeronautical or, you know, sort of like astronaut-y types, maybe you would have seen series, or maybe you've taken an astronomy class. Hey, it's an asteroid, and it sort of shows up every so often, and we see it in the sky. And series actually gave a famous mathematician, a guy named Carl Friedrich Gauss, the opportunity to figure out a method with a data set that he had just done on paper. Okay, so the story is this. There's this asteroid where a Dutch astronomer said, okay, there it is. And at midnight on a particular day, he sort of identified where it was in the sky, you know, the azimuth and the declination and all those fancy words, and writes it down. And on the next day, at a different point in time in the night, I guess the next night, he writes down the location. And he has this map of here, there, 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 there. And eventually he's staying up late at night, and he's checking late at night because he can still see Ceres, but Ceres is progressing across the sky, and he knows that he's going to not see Ceres like tomorrow or like the next day. And so what he says is, okay, there's this issue here. I know where Ceres is, and I know where it's been, but where's it gonna be when it is next visible? When it comes back around again. And I think from the path that it's tracing across the sky, you should be able to figure it out, okay? So he sends all the data to Gauss, you know, in the form of a letter, and says, okay, dude, where is it gonna be next in the sky, and what day should I look in that spot? And so Gauss takes this method that he invented for fitting a straight line to data and extrapolated out and said, okay, when it next is going to appear is just after sunset on such and thus date, and here's where you should look. And lo and behold, that's exactly where Ceres was seen next. So yeah, late 1800s, I'm sorry, late 1700s was when the method was invented. Early 1800s is when it was used to spot series, and it's sort of a cool, fun story. So there you go. We'll tell you another story tomorrow when we introduce the method called regression or fitting a least squares trend line. But that's for tomorrow. So I'm going to stop the share, and I'm going to pause the recording in a second. But y'all be free to go. Office hours are going to start in about 10 minutes. But if you got any quick questions before, then now's a great time to ask, because otherwise you have to sort of re-log in a different meeting.
I had a quick question.
Sure,
For
yeah.
the exam, could we also use Python to plot?
Yeah, you can. And if you're going to generate a plot, okay, and include that in your exam, just be sure to upload it into something which you could then display as a PDF and upload the PDF.
Got it.
My
Okay.
bet is that you won't want or need to do that,
Yeah.
because everything that I'll put on an exam, I'll put on the exam in such a way that you shouldn't need to do any analyses of the data, or you shouldn't need to use the software at all. You're welcome to use it as a tool anytime, but it is never a requirement. So students that spend way too much time with the software on the test have lower scores usually than people who spend a little bit less. So don't get too hog wild coming up with new analyses that have never been, that I didn't provide to you.
Okay, thank you. Oh, and quick question. Is the exam going to be more focused on the homework problems or the labs?
Yeah, so I can't say I haven't written it yet, so I should write that soon. I can say that the sample exam questions correspond to the sorts of things I like to ask you about. And so you'll see that the lab questions and homework are more designed to allow you to grapple with concepts. And then the exam questions are more focused on, can you apply the concepts? So hopefully that'll be helpful. And as you look over the sample exam questions between now and tomorrow's class, you'll get a sense for what that's like.
Thank you.